All right. Welcome everyone to the final day of the IAIFI workshop. So this morning, our first speaker is going to be Jim Halverson, who is one of the original founding PIs at the IAIFI. He's our leader at Northeastern. He's also someone that works a lot on the neural network quantum field theory correspondence, and I believe that is what he's going to be talking about today. So get away, Jim.
Hi, everyone. Great to see you. Thanks for being at my talk the morning after the lovely dinner last night. And I'm sure there were shenanigans that were had afterwards. So it's really nice to see people here. I'm going to tell you about some work that is coming out next week. And the key word in this title, if you've been paying attention at all to what my group's been interested in the last few years, the key new word here is conformal. In this community, I'm really happy that I don't really have to work too hard to explain what a neural network is, which is something I'm very used to in theoretical particle physics. Field theories, many of you are familiar with, or at least in some context, you're familiar with important uses of them. But the conformal part might be a little new, so I'll try to explain that. This is not advancing. What's that? There we go. Yeah, all right, good. So I've been working on this line of research for a number of years with a number of people that are connected to IAIFI. This was especially done in collaboration with Anandita, who this was part of the PhD thesis. The work today is with Joydeep, who is a student of my colleague Ming Bao at Northeastern, and my former student, Tian, who is now a professor in Shanghai. So the setup of the talk is that there's three key points that I want to give you at the very beginning before I tell you about what we're doing. Sort of just why neural networks and field theory generally, what is conformal field theory and why should you care? And then I'll tell you about something called the embedding formalism, and any different subfield of physics probably has something called the embedding formalism. There's many different notions of embedding formalism. I mean the one that arises in the context of CFT, and it's based on an idea of Paul Dirac, where he made the bold statement that Lorentz symmetry is equal to conformal symmetry. For those of you that are familiar with conformal symmetry, but not the embedding formalism, this may seem a little obscure and unusual, because a priori they seem like very different symmetry groups. So this is the key thing that sets up our work. Wow, getting used to the clicker. All right. So the essentials of our formalism is what I'll address next, including a new construction of conformal fields. This is the main takeaway of the talk, a new way to do CFT. So that's the point. And given that the essentials of the formalism, I think at this point in the talk might actually be the point where I hit the 30-minute mark, and there will be all sorts of applications that you can ask me about, examples, free theory limits, how deep neural networks and recursive CFTs come into the game, and also free bosons and mixing. But I'm gonna, given the breadth of the audience, I'm gonna try to go slow and really nail these. So the setup is three key points. What are neural networks and field theory, and what do they have to do with each other? What is the big picture of conformal field theory, and what is Dirac's embedding formalism? So neural networks and field theory seem like a strange thing a priori to put together, but in this community, we've heard some of these infinite width talks already, and Yoni in his talk yesterday alluded to sort of field theoretic ways of thinking about ML. I'll be going the other way, thinking about ML ways to think about field theory. But for the purposes of this talk, I'm always going to be taking scalar neural networks, so the outputs of the network are going to live on the real line for simplicity. So the network is just living in the space of maps from RD to R. Sometimes this dimension might change, but it'll be pretty clear on context. And crucially, the parameters of the neural network at initialization are drawn from some distribution that is part of the hyperparameter choice of whatever you're doing. But the basic point here is that the network architecture, together with the distribution you draw your parameters from an initialization, define an ensemble of neural networks. And you can compute the expectation value of the network outputs or products of the network outputs in that distribution, if you'd like, by integrating against this parameter density. So it's just some neural network evaluated on X or Y, and you integrate against the parameter density and so forth. So this is a statistical setting in which neural networks naturally arise. And the key thing is that they give us expectation values, moments of the distribution of function outputs, and we can think of this as a correlation function. And of course, in this story, this is sort of an initialization story. You can add dynamics and talk about how learning arises in this context. I'm going to suppress that here, but this is sort of the basic story, that the statistics that are intrinsic to the neural network information give us a notion of correlation functions. And that's relevant because correlation functions are the central object in field theory. So this essential neural network information that you specify whenever you start up your computer is some architecture for the neural network that is just encoded here. And then there's some density that you draw your parameters from an initialization. This is bread and butter to everything we do. And the key point is that this defines a field theory. The partition function of the field theory can be written like this in sort of a parameter space description way, where if you'd like these correlation functions that I have here, I can get by taking the partition function, hitting them with d by dj, and then setting j to 0. This is the normal way in field theory that you take a partition function and you use it to generate correlation functions. Okay, so the correlation functions are the things that we're generally going to be talking about, not the partition function. But the essence is that this information, when you plug it into this formula, defines a partition function and therefore correlation functions and therefore. This is not the way we normally do field theory. The normal way we do field theory in quantum field theory 1 is this way, which is Feynman's path integral. There's still this business here where there's this J phi term, but instead of having parameters that appear in the architecture and integrating over the density of parameters, you have some density on the function space itself according to e to the minus action. Okay. So these are two different descriptions of a field theory, and in some cases we can make these two different descriptions touch and get to know each other. I should say also that at this point that it's relevant that one of the reasons we like doing this is that in some cases it enables exact non-perturbative calculations that are not the sort of thing that we would normally be able to do. So that's part of the interest. So given that basic setup, you might ask, can I engineer this defining data? Remember throughout that the defining data is the choice of neural network architecture and the choice of distribution and initialization. Can you choose the defining data to get this simple field theory that I have and then give it some extra property that I just naively call X? And X might be quantum. Yoni raised this yesterday. I'd be happy to talk about what I mean by quantum here. You might want a Lagrangian, a local Lagrangian description of the theory. You might have some other notion of locality. Maybe you want X to be some symmetries, because in general, we don't like just field theories. We like field theories with particular properties because we're trying to describe some particular system. And the point is that once you specify your X, it turns it into an engineering problem. And so here X is equal to conformal symmetry. We're going to be spending today talking about conformal symmetry. Okay, so what is conformal field theory? Having told you a little bit about field theories and neural networks generally, I want to tell you about conformal field theory. So it's a field theory with the conformal group as a symmetry. That is, the conformal group is the group of coordinate transformations that leave the metric invariant up to an overall scale factor that can depend on the position in spacetime. The group of a conformal field theory in d dimensions, in d Euclidean dimensions, is S of d plus 1, comma 1. And it's made up, if you're asking, how do I think in a simple way about what this conformal group is? Well, it's the rotations and translations that you know from sort of Poincare invariance from normal field theory, but it's also scale transformations and something that I don't really need to talk about too much. These are what people might think of as the weird ones, something called special conformal transformations, okay? So the conformal group is made up of rotations and translations that we know and love, scalings, which is related to scale invariance of the theory, and then these special conformal transformations. And the reason that we're interested in this physically is that phase transitions are described by conformal field theory with certain universality properties, in the sense that there's conformal field theories and those phase transitions are characterized by certain scaling exponents, and many different physical systems have those scaling exponents, the same scaling exponents, which is the notion of universality. So an example of such a phase transition is the liquid to gas phase transition. I typed in the GPT, give me the Charles River starting to boil, okay? And this is what it gave me. Interestingly, if you look here, there's snow on the ground, so it's winter, so it's actually near the triple point. But the liquid gas phase transition is one example. And if you go to textbooks on quantum field theory, when they start discussing CFT, they'll give you this universality class of the liquid gas transition that comes from some appropriate thing called the Wilson-Fisher fixed point. And there's many other systems that are also described by the Wilson-Fisher fixed point. So conformal field theories are about describing phase transitions, they're scale invariant theories, and from a practical point of view, you can just think of it as a field theory that has this particular group of transformations. I'm sorry, I'm still getting used to this clicker. The other thing that is important to say, and this is when people are giving faculty job talks, trying to convince people that they should hire someone focusing on CFT, this is the picture that they show, and it's a very nice picture. So conformal field theories, because they are scale invariant field theories, they are fixed points of renormalization group flows. So when we do a renormalization group flow in physics, the perspective is that you start with some CFT in the ultraviolet, you do some perturbation of it, you follow the renormalization group flow along some trajectory, and it ends at a conformal field theory in the infrared. So this is the picture that conformal field theories are important because if we think abstractly about the space of quantum field theories, these are the bookends. These are the fixed points, and all of quantum field theory is just some RG flow between two CFT fixed points. That's the perspective. There's another reason, very theoretical, in addition to the experimentally motivated ones for why this is important. Okay, so where does Paul Dirac come? So he says the conformal group is SOD plus 1, 1. So if you have a d-dimensional Euclidean theory, this is what the symmetry group is. This is the conformal group in 2 dimensions. He also points out that is also the Lorentz group in d plus 2 dimensions, the basic fact. And therefore, he says Lorentz equals conformal. Now, obviously, going from d dimensions to d plus 2 dimensions and equating symmetry groups is going to require some sort of relationship that takes you from one set of dimensions to another. But this is the upshot of his idea that Lorentz is equal to conformal. And there's this nice paper from 1935 where he works out a lot of this. He was not thinking about conformal field theory at the time because field theory wasn't understood at the time, let alone conformal field theory. But what he was interested in was this relationship between the Lorentz group and the conformal group. So the key fact for the experts in the audience to use the right technical terms, Lorentz transformations in d plus 2 dimensions induce non-linearly realized conformal transformations on a d-dimensional projective null cone. I'll tell you in just a moment what the projective null cone is. But if this is true, that Lorentz is equal to conformal, when you swap up the dimensions somehow, you better be able to map all of the Lorentz generators to generators with conformal groups. And that's exactly what's the case. So in the coordinates that I'm using here, I'm using light cone coordinates. So I and j indices run from 1 to d. These guys are rotations in d dimensions. Plus and minus are the appropriate light cone coordinate indices. So L plus minus gives scalings, Li minus gives special conformal transformations, and Li plus gives translations. So this is the sort of map between conformal transformations and Lorentz transformations that was worked out in his work. I should mention a little bit about the way that this embedding space works. The embedding space in the projective null cone, so I need some d plus 2 dimensional space. This is just d plus 2 dimensional Minkowski space. Throughout, little x is a vector in Rd. Okay, so it's a d-dimensional vector. So this is some d plus 2 dimensional thing. Here's the time direction in Minkowski space. Here's an extra spatial direction. And what you can do is you can say, I'm going to do 2 things. To go from d plus 2 to 2, I have to reduce, from d plus 2 to d, I have to reduce 2 dimensions. The first thing that you do is that you start in d plus 1 and you go to the null cone. These are the vectors in Rd plus 1, 1 that are null, that have x dot x equals 0 in the Minkowski metric, capital X dot capital X. And throughout, capital X will always be my embedding space coordinates, and little x will always be my Rd coordinates. That only gets rid of one dimension, though. To get rid of the other dimension, you do something called projectivization, and then you do something called choosing the Poincare section, which is some technical thing that I don't need to get into. But after passing to the null cone, projectivizing, and choosing the Poincare section, your coordinate in d plus 2 dimensions looks like this. But you'll realize when you just count the degrees of freedom here, all of the degrees of freedom are in this x vector. This is x dot x here. So really, this way of writing this coordinate in d plus 2 dimensions is just some effective d-dimensional subspace. And in fact, it's a copy of Rd. Okay, so this was his idea. And in fact, you can work it out in more detail than I will here. One of the key things is that some of the Lorentz transformations actually take you off of the Poincare section. And the nonlinear realization of the symmetry is what you do to bring it back to the Poincare section. But this is a common story in the CFT literature, and I should mention that this is not something that is new to CFT. We are not bringing this. This is literally textbook CFT. Good. So in modern CFT, the embedding formalism is something that people do in modern CFT quite generally. And their idea is they want to take this idea and they want to think of some conformal field that they have in d dimensions. And they want to lift it to d plus 2 dimensions, and it has to satisfy certain constraints. So what they have is they have some conformal field that they want to lift to d plus 2 dimensions. It depends on all of the d plus 2 dimensions here. It has to be homogeneous. That's important. And then they get their conformal field back by taking the field in the higher dimensional theory and restricting it to the Poincare section. So with part of the reason they do this is that they're interested in understanding the correlation functions in their CFT from the point of view of Lorentz invariance. So the conformal symmetry is a rather complicated symmetry compared to Lorentz symmetry, and they want to bootstrap what they know about Lorentz symmetry to better understand CFT. That's what they do. So this sheds light on new light on conformal objects, for example, the correlation functions. And in particular, when writing it in this way, for example, the 2-point function in the embedding formalism is of the form x1 dot x2 dot here. Whenever I write capital X dot capital X, that's a Lorentzian dot product. So this is a Lorentz invariant thing. I have some Lorentz invariant 2-point function. But when I use this map and I pull it down to the Poincare section and reducing the theory by 2 dimensions, it turns into a conformal field with the right transformation for a conformal field. Okay. So this is how the essentials of the embedding formalism works. And the key thing is that I can take my correlation functions of higher dimensions and pull them down. Okay. Finally, one thing that I'll mention is that there are something that I'll write later called U and V. They're conformally invariant cross ratios. U and V are totally conformally invariant. So it turns out that one way that you can parameterize the 4-point function, which is the thing that encodes the leading interactions in the theory, is that you can parameterize it by pulling out this combination of particular coordinates. And then GUV is this fully conformally invariant thing that completely determines the 4-point function. Okay, so this is the embedding formalism. The embedding formalism is a powerful tool for understanding CFTs, understanding how conformal invariance constrains correlators of known CFTs, or CFTs we're searching for with constrained optimization. People in my community call that bootstrap. The bootstrap is an extensive and important program to try to understand CFT better. But from a practical ML perspective, it's constrained optimization. Okay, so they're solving a constrained optimization problem that's very important physically, and all of this embedding formalism shows up there. But you might ask, can we use this embedding formalism to actually construct conformal fields? And this is the thing that, to my knowledge, has never been done and that we're going to do today. So the essentials of our formalism are the following, and it's actually pretty simple. I think the novelty here is that it's something that puts together things from different communities in a very simple way to do something new. This is based on something that I think will come out next week. So we're asking this question, can we use the embedding formalism to construct conformal field theories? And the basic idea is this: if we can somehow, instead of taking a known CFT and lifting it to the embedding space, if we can somehow find a way to construct a Lorentz invariant homogeneous field theory in d plus 2 dimensions, then if we restrict it to the projective null cone, we obtain a conformal field theory, or at least a conformal field on R and D. This is the essentials of this construction. Build something here, push it down, and get a conformal field. To do this, there's 3 very important constraints. There's homogeneity, which is the condition that I showed you previously, that when you do a scaling of the input, it scales through the field with some scaling dimension. It's power law. There's Lorentz invariance. So because Lorentz invariance here is related to conformal invariance here, I better have Lorentz invariance up here. This is the crucial symmetry in the construction. And Lorentz invariance is easier than conformal invariance. So the whole idea is to bootstrap the relative ease of Lorentz invariance to get a CFT. And finally, the other thing that you need your correlators to be well behaved. For me, a minimal definition of a field theory is a theory with fields and correlators. Okay, so I'm going to have fields and I'm going to have correlators, and the correlators had better be well behaved. And these are, as far as we can tell, the only 3 constraints that we have to impose on this theory. But that's what we're going to do. So principle 1 is homogeneity. So the idea is just let phi be a neural network with a homogeneous architecture. That's something that's easy enough to do. This is the only property that needs to be satisfied. This can be literally any neural network, as long as when you multiply the input by a constant real number, it factors through with some scaling dimension. For instance, you could just take an NLP with a homogeneous activation function and you're done. That's already sufficient. But writing down a homogeneous neural network architecture is a very easy thing to do. There's some technical points that I don't know that I have time for, but I invite comment on them. Alternatively, something you could do is you could say, I'm going to take compositions of homogeneous polynomials. Homogeneous polynomials are famously homogeneous. And of course, there's a lot of math that backs that up. From an ML perspective, something that's interesting about this is it hurts expressivity. You may remember in standard universal approximation theory for MLPs, if you use a polynomial activation, it is not a universal approximator. The polynomials are somehow bad for expressivity. You expect that. But on the other hand, if you were to do something like this, it potentially gives you increased control because we know a lot about homogeneous polynomial rings. And in particular, we also know about connections to algebraic geometry that lets you potentially bootstrap a lot of math into the scheme. Okay, so principle 1 is homogeneity. Principle 2 is Lorentz invariance. So you can show it at the level of the partition function, but here I like to think of it in terms of correlators. These are the correlation functions of the theory. These are the things, very roughly, if one wanted to think in a particle physics way, these are the things that are the analogs of amplitudes. And we have them computed in parameter space where capital theta is the parameters of my neural network. These are the things that I need to be Lorentz invariant. But we know how to do parameter space symmetries in field theory. The basic idea is that you choose an invariant probability density for your parameters. You do some transformation of the fields under the symmetry. So in particular here, you'd be doing a Lorentz transformation of x1 through xn under some fixed Lorentz transformation. You absorb that into a parameter redefinition. And if P is invariant, then that parameter redefinition leaves the correlation functions invariant due to the invariance of the mesh. Okay. So this is a very, very simple mechanism to engineer all sorts of symmetries in these neural network field theories. This is the one that we're using here, is Lorentz symmetry, but it's doable. So principle 2 is doable. So in our case, we choose P to be Lorentz invariant. So both of the things that I just said actually sound pretty easy, and it seems maybe too good to be true so far. And so what I want to tell you is something that I think is really the big constraint, and I want to learn the pain of this constraint by considering a simple example. So the final thing after we do homogeneity and Lorentz invariance is that we need to end up with correlators that are well enough behaved that don't diverge everywhere. So the natural idea is to take to get a Lorentz invariant P by whip rotating some famous rotationally invariant probability density. Does anyone have a favorite rotationally invariant probability density? Yes. Multivariate Gaussian. Here it is. Here's my favorite rotationally invariant probability density. I'm going to change it up by doing a whip rotation on the 0 components. Sounds good. I will end up with something that's Lorentz invariant. This is how whip rotation works. And then you get this, and it's a wrong sign Gaussian. And you, first of all, cannot interpret this as probability anymore because it's not normalizable. Yeah. And second of all, more importantly for our construction than the absence of a probabilistic interpretation, is just the fact that this thing being under the integral in the correlation functions, right here, causes everything to diverge. Okay. So that's the pain. And in some sense, the difficulty in this construction and what we've been working on for the last little while is overcoming this technical difficulty in different ways. But homogeneous and formal Lorentz invariants are quite easy by a clever choice of architecture and choice of probability density, but getting the correlators to be finite requires some cleverness and carefulness. And so this is where the actual story requires some work. In the sense that, like, example by example, you have to make sure it's true. The general formalism makes sense. So just to recap the formalism, and there's 7 minutes left, and then we'll see where we go from there. We have an SOD plus 1, 1 symmetric homogeneous theory on RD plus 1, 1. The idea is, this is just some list of features. Maybe you're not familiar with all of the features, but if I can engineer this theory and push it down, I can get a conformal field theory on RD that can potentially describe some phase transition. The constraints that are crucial on this theory is homogeneity, but we're just going to get it by having a homogeneous neural network. Lorentz invariance arising from an invariant P of theta, and correlators where we compute in parameter space and we work to make sure they're well made. Okay. So this is the formalism. This, if you like, this is the meat. One thing that I would say is if you ask, if CFP people know so much about the embedding formalism, why haven't they tried something like this before? And as far as I can tell, the key thing is that when we specify field theories, we normally don't specify the functional form of the fields that we're considering. That's the key thing that when we specify a neural network we're doing. We're specifying the functional form. We're saying the class of functions we are computing, we are working with looks like an MLP or a transformer or whatever it might be. Normally in field theory, we say, here's my action, and that defines a probability density on the space of functions, but it doesn't actually tell you directly about the functional form of the field. And that's why, at least an action-based description of the field theory, you couldn't do this. So to be able to ensure that the fields are homogeneous, which is trivial once you let yourself specify the form, this is the thing that looks a little obtuse from a normal field theory perspective. And I think that's why we're getting some leverage. Okay, so that's the formalism. That is a cake with a little bit of icing. And, you know, of course, I'm not done with this story. I haven't given you a single example yet. This is my decorated cake. The rest of the talk is just to go, like, the meat, I've really already given you the key conceptual ideas that are really new. And the rest of the talk is just to put various decorations on it. None of these are essential decorations for the construction. They're just interesting things that can happen. Are there any like real mathematicians in the audience? Okay, so real mathematicians love, like, if they don't like you, they call your result a lemma, right? But generally they like to think of lemmas as those like little mini results that might not be that interesting on their own that lead to big theorems. And then once you have a big theorem, you have a corollary, okay? So in math language, like, this is the theorem, and what's coming after this is just a bunch of corollaries. So there's a simple pedagogical example. There's a clever example. There's a generalized free theory limit that I will take. I can then ask, what if I want to do this story with deep networks instead of a single layer network? These first two will be single layer networks. And what you can find there is that you actually get sort of recursive conformal fields with the CFT defined at every layer. And then we'll talk a little bit about the free boson and mixing. I only have 4 minutes left. Maybe with those 4 minutes to really end on time, what I'll tell you a little bit about is just these two examples. I encourage you, if you're interested in free limits or deep nets and recursive CFTs or the free boson and mixing, to ask me about them in the question section. But let me give you 2 simple examples to just prove this first. This is a dumb example, okay? The point is pedagogy. So what I'm going to do is, in this case, I'm going to start with a D+2 Euclidean theory with full rotation symmetry. I'm going to compute all of the correlators of this theory exactly right here. I'm going to wick rotate to D+1, and I'm going to push down the projective null cone and get a CFT. So we solve the Euclidean D+2 theory. We wick rotate to the D+2 Lorentzian theory, and we push down to the CFT. So I'm just going to take a silly little architecture that is theta dot x. I'm going to take theta to be rotationally invariant. When you write down the correlators of this, because it's linear in x and we just have a dot product here, you can actually factor all of the inputs to the neural network completely outside of the expectation, and you just get a moment tensor. And that moment tensor basically contracts things according to the contraction. So what you get is a Euclidean theory where you can compute all of the correlators analytically. When you whip rotate, the Lorentzian theory has correlators of this form, where this is now the Minkowski contraction. Notice that this thing that I compute in this simple example is completely Lorentz invariant, right? And then when I push it down to the projective null cone, that construction turns these capital X D+2 Lorentzian coordinates into little x CFT coordinates. And for example, I get a 4-point function of this conformal field that when I do the S channel way of pulling out the input dependence, I end up with this function GUV that completely characterizes the 4-point function. This is totally exact in this simple example. And what I get is that GUV is this particular combination of U and V. And for the experts in the audience, at this point, you know, a CFT person will be like, well, I'll do a conformal block decomposition. And you can do it. This thing is completely conformally invariant. And I get, in this very simple example, an exactly computable at all points in the correlators CFT on the projective. Something that is less trivial, one thing to say here is that the scaling dimension here, because it scales with a positive power, yeah, this does not satisfy the unitarity bound, which means it does not satisfy a necessary constraint to have a unitary theory. So this is a CFT, it is not a unitary CFT. To do that, you need to flip the sign, and so we just take the architecture from the previous case, we flip the sign, and we write a P of theta of this form. Note that this is not technically a probability, because theta squared, this is the Minkowski contraction. And the Minkowski contraction, I can have this be less than -1. And so when I add them up, I get negatives here. But that's fine, because I can still write down the correlators, and you can ask, how can I potentially evaluate the correlators? And if you look at this, particle physicists in the audience say, okay, remembering that this is over D+2 dimensional Minkowski space with a theta squared contraction, this is something that looks like the propagator that would appear in a one-loop Higgs calculation, where the role of theta, the role of the momentum is played by theta, and the mass squared has been set to 1. So we know how to do integrals like this. You can just dim reg this or use whatever favorite technique you want. And more generally, this sort of motivates the spirit of how you compute these correlators. I write down the correlators, which by construction are conformally invariant. I need to be able to evaluate them. And what we do in the paper is there's something in the amplitudes community called integration by parts identities that let you write finite integrals as differential equations. And if you can solve those differential equations, you have the exact result. So that's what we do here. We compute the exact 4-point function. Its associated GUV is of this form. It's completely conformally invariant. It satisfies crossing, and you can study the spectrum and infer properties of it, etc. Okay. So those are the two examples. I have 10 seconds left, which is the perfect time to go to my conclusion slide, and then invite to talk about whatever you want. The key thing in this talk is that we tried to come up with this thing that I've been interested in for a while of using neural network and ML ways of thinking to do field theory in a new way. We said today we're going to try to do conformal field theory. And the way that we're going to do it, because constructing a CFT directly here is hard for reasons I'm happy to get into. But if you can do it using Dirac's idea of starting with a Lorentz invariant theory 2 dimensions higher and coming down, then you get a new way to do CFT. Something that I would point out that's interesting is that this theory does not have to be translation invariant. So this is a homogeneous Lorentz invariant theory that does not have to be translation invariant. Because what you need is translation invariance here, and because Lorentz equals conformal under this reduction, the translation invariance here comes from Lorentz transformations up here. And in particular, the theories that I showed you were Lorentz invariant, but we're not conformal. Sorry, but we're not translation invariant. The constraints are homogeneity, Lorentz invariance, and then making sure your correlators don't blow up too much. And then we have this decorating the cake where I gave you these two examples, and I'm happy to tell you about deep nets and recursive CFTs, free bosons, generalized free limits, etc. But Dirac taught us that Lorentz equals conformal, and this is something that I've been interested in using for a while, because in this program of trying to do field theory with neural network ideas, we want some like stakes to put in the ground, and one of the stakes that people in my community are interested in is CFTs. Okay, thanks a lot.
Any questions? This is really a very basic question, but I mean, maybe the reason that we haven't constructed QFTs using a parameterized form for the field is that that needs to be very infinite dimensional. And if you have a finite number of parameters in your neural network, you're not going to be able to get the entire function space. So does all this need to be, strictly speaking, done in the infinite limit? And if that's the case, then how you actually you want to compute correlation function numerically by putting up some neural network on your computer, how are you going to do it?
Good. Let me take those questions one at a time. I'll probably ask you to repeat the second question in a second. So the first question has to do with sort of the infinite dimensional nature that we normally do in QFT. That is something that is true in our standard QFT descriptions. And if you wanted to take this story on the map out of there, you're taking the infinite with limit and you're inducing interactions by inserting an operator, and you could even insert a local operator. And for example, our result from last year was 5-4 theory, bang on, infinite width, where we understood how the insertion of the local operator was affecting the story. I do think it's perfectly well defined to talk about finite dimensional function spaces and their correlation functions. What word you attach to that is a different story, but I have functions which I would call fields, and I have correlation functions. One thing that I might add is that, okay, so I'm a string theorist, and we talk to mathematicians a lot, and mathematicians love complaining about how the path integral on infinite dimensional function space is simply not well defined. We normally ignore them and move on with our lives, and you say things like, great, take that thing, put it on a lattice, then it's just a joint multivariate probability distribution, everything's fine. What are you talking about? Don't worry. But the question's an interesting one. Definitely at finite width, finite number of parameters, it is a finite dimensional function space. And understanding how that fundamentally limits what these theories can and cannot do, and whether it's something that's a feature rather than a bug, is something I don't have.
Okay, so you want to, so the feature rather than the bug is you want to regularize the path integral in function space and not in coordinate space.
Mathematicians that care, which is it's only some, will sometimes tell you that path integral in the continuum simply is not well defined. What are you talking about? And I think that this finite dimensional neural network way of doing it, regardless of whether it's useful, which we can talk about, it's definitely well defined. It's just some finite dimensional normal integral. That integral d theta is a normal integral. It's not a function. What was your second question?
Oh, just like, if the finite dimensionalist bothered you, then how would you actually compute correlation functions numerically? But I guess you said it doesn't bother you, so
Good. At finite width, the way that I would compute correlation functions numerically is just a sample.
Right, that's what I mean,
Number of
yeah.
parameters, yeah, and, yeah.
So that's what you want, that's okay.
If that's what you want, yeah, absolutely. And at infinite width, I can still do calculations, as your talk emphasized. You can't do infinite width calculations by putting them on a computer and sampling an infinite number of parameters, but you know, you can still do calculations. Yeah.
I put talk to. I'm going to do a little bit of free association. So you mentioned CFTs basically characterize phases of the system.
Yes.
And this kind of reminds me of grokking in ML.
I love grokking.
So do you think this can be applied to understand grokking? Because when I kind of squint and stare at it, it looks like a phase transition.
I guess I don't have a useful comment. It would be interesting if it could. To broaden beyond grokking, there is a question of what this is useful for in ML, right? If my focus here is for field theory, but since we're in the process of understanding conformal fields, you could ask if that's useful for ML. Generally in ML, we might be more concerned just generally with scale invariance, not specifically with conformal invariance. And as you know, the difference between scale invariance and conformal invariance is something that is well studied in high energy theory, and unitarity is a crucial thing that makes them equivalent. But in non-unitary theories, they're not equivalent. And it seems to me that in ML settings, more generally, what you're going to want is scale invariance, not conformal invariance, unless you really require the extra symmetries and special conformal calculations. But as for grokking, I don't have a specific comment. Sorry.
Thank you.
Okay, thanks, Jim, from the next one. So just wondering if you can say a few more words about how you deal with Lorentz invariant probability distributions, and how do you avoid the singularity, or I guess a more concrete question is in that example where it looks like a propagator, and then how do you know which branch to take? Like, are there different physical interpretations of different branches?
So here we're just doing normal BIMREG, and really honestly what we're doing is, are you familiar with this differential equations for finite intervals story?
Not really.
Okay, so what the amplitudes people do, there's Johannes Hahn wrote a really nice lecture series like 10 years ago that's called Differential Equations for Finite Intervals. When you do DIMREG, there's something called IDP identities that take your finite intervals and relate them to each other. There's a notion of something called a master interval. And you can rewrite your finite interval in terms of master intervals, and even write down differential equations that your finite intervals need to satisfy, such that if you can write down those diffie-qs and solve the diffie-qs, you can do your finite interval by solving a differential equation rather than by doing the integral. And that's the technique that we use. The thing that was a little bit painful about this is that there's packages that do it, but we're outsiders to the community and we've never done these calculations. So we had to do like 10 pages of calculation by hand in glorious detail. But the amplitudes community has developed nice software packages that use these techniques. It's all built on integration by Kautz identities coming from DIMREG.
So how does the I epsilon come in here?
So how does the what?
I epsilon. Because that tells you which branch to take in a normal loop integral, right? And here it seems like a very different context, so I'm not sure if the same.
Yes, I think it's under the hood in the formalism, but I'm actually not sure where they deal with the I epsilon. To say more generally, you called it a probability. I would crucially say that, and remind us that in Lorentzian field theories, yes, in Euclidean field theories, e to the minus s is a probability density on some function space that mathematicians might complain about. And if you put it on the lattice, it's a joint probability distribution. In Lorentzian theories, I don't think we should be shackled by thinking of them necessarily as probability distributions, because in normal Lorentzian functional descriptions, it's e to the is, which is definitely not a probability density. So that's why we sort of let ourselves consider this thing, which is definitely not a probability density, but nonetheless, if you can do the integrals, you have notions of correlators that you can do in this thing that's not a probability density. It is true you can do rejection sampling to make this greater than -1, and in that case, it does become a probability density, and we're starting to sample that and do Diracs and so forth. But in the Lorentzian cases, I would encourage us to think of P of theta as a more general object that arises in the integrals, and in some cases might actually be a probability.
More questions?
Yeah, thanks a lot for this very interesting talk. Just from a more practical standpoint, can you give an example where homogeneity is like a desired property of a neural network? I think it's very intuitive for things like translation invariance and all this
Yeah,
invariance, but what about the homogeneity?
Yeah, I forget some of this story a little bit. There's relatively little said, but there's sort of a story of deep information propagation and sort of having things be nice and scale invariant through a network, and talking about criticality there. And in particular, in Dan and Shou's book on principles of deep learning theory, one of the things that they talk about is taking homogeneous activations. They're after just scale invariance, not full conformal invariance like I am. But the idea is that because scale, this power law behavior is related to criticality, that it's something that you might put in. But you're absolutely right. It is not something people typically do. This is something that ML theory people are using as sort of an organizing principle to understand, perturbations of different activation functions around perfect power law. I don't know. Yoni might have more to say, but
Okay,
that's my understanding.
Thanks, Noah. I have tons of questions, but I probably have to talk about the copyright, but I think I want to understand something kind of basic. You kind of threw this theta in there, and theta itself transforms onto Lorentz group. So theta is itself a parameter that has well-defined transformation properties, at least.
If you choose to transform it, but in this case, I'm not choosing to.
You're choosing not to so
You're asking how Lorentz invariance arises.
That's right. Well, I'm asking how Lorentz invariance arises, and the follow-up question is, what was stopping you from doing exactly the same kind of relatively simple story for just Poincare invariant field theories? What makes that more complicated? You emphasize the value of just having to deal with Lorentz symmetry and not having to deal with the full Poincare group. And I think I'm not understanding.
Oh, yeah.
And so I think that it's tied to what are the transformation properties of theta itself.
Yeah. So the way that this story normally goes, and it was inherent, we sort of wrote down a more general story from the ML literature. But if you have the parameters in the neural network and you're choosing to, find the symmetry page. Right. There it is. Okay, good. Okay, good. Okay, imagine that phi is theta dot x here, and I am not transforming theta a priori whenever I do a Lorentz transformation. So I have phi theta of x. Theta are just the parameters that are describing, its fluctuations are describing how the field fluctuates. When I transform x transforms. And so I have phi of Lx in here, but because the architecture is theta dot x, that transforms to theta dot Lx. And you can think of the mechanism is basically that you can think of that as an effective redefinition of the parameters, where theta prime is now theta times L. And if the parameter density is invariant, that redefinition leaves the correlators completely invariant. So this is a situation where x is transforming. Theta is some integration variable in the correlators that is not external. It's not transforming, and it's the absorption and the redefinition that gives you Lorentz invariance of this object. Your other question is about Poincare invariance. Translation invariance is a little bit hard. So I'll ask a related question that I sort of prompted. You said, why not just do the full translation invariant thing here? One reason is that you don't need to, because translation invariance here comes from Lorentz transformations up here, and that's known. But the thing that I was after for a while before I started talking with my new collaborators on this is that I just tried to do CFT directly here. And I knew how to do translation. I have a paper in 2021. I knew how to do translation invariance and rotation invariance. Scaling, not that hard to get, but getting scaling while you preserve the translation invariance was the thing that didn't happen. The mechanism that I know for translation invariance in a very simple, straightforward way is with a non-homogeneous activation function, and that breaks scale transformations. So there may be a way to do it. You could come up with another way to do conformal fields from neural networks, where you just engineer the CFT directly here, but I don't yet know how to put together full Poincare invariance together with scale invariance and then work in special conformal. And the nice thing of this formalism is that you get it all from Lorentz.
All right, any last questions? If not, let's thank Jim.